What is RMS current? It is the equivalent of the DC current which will produce the same heat. That's all. Okay. So very interestingly, this number matches with the experimental values. So we are studying R only. So what it means is, let's say I have a resistor and then I am giving a AC current. Okay. So in the battery example, right, we must have done some kind of experiments, right? So energy is given from here or is it given from here? Energy is given from supply, right? And this is resistor. So resistor consumes the energy. The battery or the supply gives you the energy. Here, that means if I am giving 5 joules here, it will be consumed here. Kirchhoff's law, remember? So whatever energy I am giving here, it's coming from, whatever energy which is consumed here should be coming from here. You agree? So that means if I take this point here, right? So what I am giving here, E is equal to E naught sin omega t. What is E? E stands for EMF, right? Voltage. I told you whenever it is consumption of voltage, we call it as V, voltage. Whenever it's supply, we call it as EMF. Okay. So if I put my voltmeter between this point and this point, it will be called as VR. Okay. So if I said this is equal to this, do you agree with that or not? Whatever energy I am supplying is what is going to be consumed here, which means this is equal to this. Okay. So in Kirchhoff's law, loop wise, if you go by the loop, you would put the E on one side and then all the consumption on the other side, right? Which means E will be on this side, VR will be on the other side. So that means VR is equal to E. So VR is equal to E naught sin omega t. Okay. So if the current flowing here is I, right? The resistor is R. What can you say about VR? Current is I, resistor is R. What is the voltage? V is equal to IR, right? So this can be written as I into R. So as I told you, sometimes we write current as I like this, sometimes we write like this, so it doesn't really matter. Okay? As long as you are not confused, you can write either way. E naught sin omega t. Okay. So the main purpose here is I want to find the current, which means I want to bring the R on this side. So I is equal to E naught by R sin omega t. What is E naught, by the way? Okay. That is in the alternator, right? AC generator. Nab omega, that is different, right? So here it's just the maximum value. Maximum EMF. The curve is going like this, right? So what is the maximum value? That's E naught. So this is maximum EMF and this is divided by resistance. What is voltage by resistance? Current. So if it is maximum voltage divided by resistance, it will be maximum current. Okay. So it will be I naught sin omega t. Okay. What is the doubt? I have to ask later. You came late, so obviously you are not going to get anything, right? So take it down and sit and discuss later. Okay. So I is equal to I naught sin omega t. So that's what I wanted to derive. So you see, even though I gave this the beginning, right? So this is what we derived here. So if I say, so if I compare this and this, so carefully listen here. So E is equal to E naught sine omega t. Okay. So the sine omega t term is exactly the same. So what did I say? The shape is given by this. The value is given by this. Do you agree? So that means if I show the sine omega t curve like this, right? So I naught is going to be somewhere here. So this is sine omega t curve. So let's say this is E naught sine omega t. Okay, which means I can call this as I is equal to I naught sine omega t. Why? Because both of them are having the same sine omega t, which means the shape is going to be the same. Only thing that is going to change is magnitude, right? So the amplitude is going to change, which means all this value will change. Is that clear? So once we do the next one, it will become much more clearer. So basically, we call this as, when you are drawing it in your exams, it's better to draw it two different colors like this. Okay, only then it will make sense. Or maybe a pencil and a pen, something like that. So we say that this is my EMF, this is my current. So E and I are in phase. Okay. What do you mean by in phase? Both are rising at the same time and then falling at the same time, right? That's the meaning. Suppose if I draw a curve like this, what can you say about this one? What is the right word? It's called out of phase, right? When this is rising, this is falling. When this is falling, this is rising. So this you would call it as out of phase. Okay. This one, it is in phase, right? Both are rising and falling at the same time. Is that clear? So in fact, I wanted to show you this, but unfortunately the cathode ray oscilloscope, right? So it's costing somewhere around 40,000 rupees. Okay. So for now I thought, okay, let's just do it theoretically. Right? And just trying if there is a possibility of getting a rental oscilloscope, we can try it. Okay. So if any of you know anybody renting oscilloscopes, we can try it. Okay. Let me know. Shania, do you know anybody? No? He said Shania knows somebody. Any electronics person, okay, if you have any contacts with any electronics people, talk with them, okay, find out if they have any oscilloscopes. So you see the circuit is very simple, okay. I have to give an alternating current and I have to put the leads, and then I'll be seeing that, the EMF and the current will be going like this. Okay. So please listen here. So there is something called phasor diagram. Everyone listening? So there is something called phasor diagram. So what that means is the voltage can be represented like this. E naught can be represented as a vector. So I can say E and I can be represented as vector. Okay. So here I have shown E as black one and then I as blue. So maybe I can connect this as this blue one is. So this is E naught. This is I naught. Okay. What it means is, current, is it a vector or scalar? It's a scalar, right? It doesn't have a direction. And voltage, scalar or vector? Scalar. Voltage definition we studied in the second chapter. What is the definition of voltage? Work done per unit charge, amperes per kg, right? So work done is scalar, which means voltage is also scalar, right? So then how come we are representing it as a vector? So that's the trick here. So somebody said, if I take this as a vector, right, and if I spin it, right, it's just a trick. So let's say I have some kind of let's say I have some kind of object here. So please listen. So can you see this blue dot here? So suppose if I keep it here, so at this point, time instant t, I am going to put 0, right? Because I am looking at how much y-axis is increasing here. So when I bring it here, so it will be somewhere here. So at this point, it will be somewhere here. If I bring it here, right? So this point can be projected as something like this. And when it's here, right? So it can be projected, maybe this side is not required. You can project only on this side. You understand what I'm doing? If I go further like this, maybe I moved it a little bit. I shouldn't have done that. Okay. So here it's going to go like this. Here it's going to be. So when it comes here, what do you think will happen? That will be the maximum. So the maximum will be here. So the curve will look something like a sine curve here. So if I go further down this side, right, what will happen? It will reduce like this. If I go here, at this point it will become 0. At this point it will become negative. So it will be going bottom. So that's the meaning of this. So try to draw this along with this. So somebody said, okay, if I take it as a phasor diagram, and if I spin this, right, the E and I will be in phase, and you'll be getting the sine curve. So as I spin this, I'll be getting the sine curve. So this is E naught, right? So this point. So due to space constraint, I am leaving it like this. So I hope you can finish it up. So similarly, current will be going like this. Okay. So you have to project it from here to here. As it keeps on rotating, you will be getting the sine curve. Okay. So from the phasor diagram, you will be getting the sine curve. Okay. Why do you think I have shown the E naught and I naught exactly at the same line? Because they are in phase. Suppose if it was out of phase, right? If it was having some angle difference, which we will be talking about in the next class. So this will be like this, which means this and this will be happening at a different phase. Okay, we'll come to that later. So I hope you understood this phasor diagram and what is the importance of it. So as you spin the phasor diagram, you will be getting the sine curve. Okay. So what we have studied today is only R only the resistor. So then we are going to study L only, and then C only, and then we will be combining all the three, RLC, RLCR. Okay. So this is the important chapter.